Hi, I'm Ryan Baker, and this is Big Day in Education. Today we're going to move on from metrics for classifiers to talk about metrics for regressors. The metrics for regressors that we're going to talk about today include linear correlation, also called Pearson's correlation, mean absolute deviation and its close cousin root mean squared error, and information criteria, including the Bayesian information criteria and AIC. Linear correlation is, when A's values change, does B's values change in the same direction? And it assumes a linear relationship. So it assumes that it's not going like this. So what's a good correlation? 1 is perfect. 0 is no correlation at all. There's just no relationship. -1 is perfectly negatively correlated. In between, what's a good correlation? Depends on the field. In physics, a correlation of 0.8 is something you have to be depressed about. In education, a correlation of 0.3 is something you can be excited about. Why are small correlations okay in education? Is it just that we're inferior to physicists? I'll ask my dad, he's a physicist. Lots and lots of factors contribute to just about any dependent measure. So let's look at some examples of correlation values. As you can see, 1 is just a straight line. It can be any slope except for flat. Couldn't be this either. But as long as it's going up, it's 1. If it's down, it's -1. You can see 0.8 has more spread, 0.4 has a little more spread still, but you can kind of still see a pattern, and 0 is just a blob, and then 0.4 going the other way, -0.4 and -0.8. So as you get more close to 1 or -1, you get more focused. And you can see that all the lovely stuff at the bottom all has a correlation of 0. Now it's worth noting that correlation tells you how good a linear relationship can fit the data, but it doesn't tell you everything about exactly what the relationship is. That's why it's still good to look at a plot of some sort. Take Anscombe's famous quartet. These 4 graphs all have equal correlation, but they tell very different stories. One of them, the top left, is kind of the classic image we have for a good but not great correlation. There's a line, they're kind of spread out along it. The top right, you can see that although that line fits the data with that same correlation, actually it's completely missing the point that there's a curvilinear function. The third one is a line with the wrong slope but an outlier. And the fourth one is just junk. These all get the same correlation. So correlation doesn't tell you everything, it's just a start. R squared is the correlation squared. It's also a measure, by some fancy statistical voodoo that I won't be talking about today, of what percentage of the variance in the dependent measure is explained by a model. If you're predicting A with B, C, D, and E, R squared is often going to be used as the measure of your model's goodness rather than R. This depends on the community. It's kind of arbitrary which ones communities prefer, but you might see it. Spearman's correlation, rho, is the rank correlation, and it turns each variable into ranks. So 1 becomes the highest value, 2 becomes the second highest value, 3 becomes the third highest value, and so on. You turn the variable into ranks, then you compute Pearson's correlation. There's actually an easier formula, but it's not relevant here. Spearman's rho is popular in cases where you have lots of outliers, or a relationship that's monotonic, but not particularly linear. It's interpreted exactly the same way as Pearson's correlation, with 1 being perfect, 0 being no correlation at all, and -1 being perfectly negatively correlated, just like my Uncle Jerry's tips on the stock market. So why use Spearman's correlation? Well, it's more robust to outliers than Pearson, and it determines how monotonic a relationship is, how much one going up associates with the other one going up, not how linear it is. And sometimes that's what you want instead. A second goodness metric for regression models, actually a pair of them, is root mean squared error or the mean absolute deviation, 2 very close cousins. Mean absolute deviation is just the average of the absolute value of the actual value minus the predicted value for each data point. So for every data point, we see how far our prediction goes from what it should have been, and we don't care if it's above or below, we take the absolute value, and then we average that. The root mean squared error is a close cousin, and what that is it's the square root of the average of the actual value minus the predicted value squared. So it's very similar to mean absolute deviation, but for larger deviations, it treats it like a bigger deal. So mean absolute deviation versus root mean squared error. Mean absolute deviation tells you the average amount to which the predictions deviate from the actual values. Very interpretable. Root mean squared error is mostly the same, but it penalizes large deviation more than small deviations. So to give an example, if we have an actual of 1, 0.5, 0.2, 0.1, and 0, true data, and predictions of 0.5, 0.75, 0.4, 0.8, 0.4, the absolute deviation is going to be the absolute value of the differences. And that becomes, you can see, 1 minus 0.5 is 0.5. 0.5 minus 0.75 is negative 0.25, which we absolute to 0.25, and so on. So the mean absolute deviation is going to be the average of all of those, which turns out in this case to be 0.41. The root mean squared error is 1 minus 0.5 squared. 0.75 minus 0.5 squared, you can see it really doesn't matter, again, what direction you're in because it's getting squared, and nothing can be negative after squaring. And so the squared errors are these, and then you take the mean squared error, which is the average of these, and then you take the root mean squared error, so the square root of that, and you get something that's just a little bit higher than the mean absolute deviation. So it's counting the big deviations in this case as being more important, the 1 to 0.5 in particular, and the 0.1 to 0.8. So it's worth noting, low root mean squared error and mean absolute deviation is good. You want less deviation from the values. High correlation is good. You want high, if yours goes up, the other one goes up. If yours goes down, the original data goes down. What does it mean? Well, a low root mean squared error, mean absolute deviation, and a high correlation means you got a good model, and you can kind of go thumbs up and you're happy. A high root mean squared error, or mean absolute deviation, and a low correlation means you got a bad model. What if you have high root mean squared error and high correlation? In that case, your model goes in the right direction, but it's systematically biased. For example, let's take a model that says that adults are taller than children, but that adults are 8 feet tall and children are 6 feet tall. This model correlates well, but the root mean squared error or mean absolute deviation is a bit off. What if you have a low root mean squared error or mean absolute deviation and a low correlation? In that case, the model values are just in the right range, but the model doesn't capture relative change. This is particularly common if you don't have much variance in your data. So, which one should you care more about? A lot of people like root mean squared error better. I happen to think correlation is more important as long as your data is the right kind of data for correlation. Now let's talk about information criteria. BIC, the Bayesian information criterion, makes a trade-off between the goodness of fit and the flexibility of fit, or in other words, the number of parameters. The formula for linear regression, called BIC prime, is a function of your number of students, or number of data points, and your number of variables, and also of your correlation. So BIC prime has some nice interpretability. If you've got a value over 0, then your model is worse than expected given the number of variables. If you've got a value under 0, then your model is better than expected given the number of variables. And you can use them to understand how significant a difference is between two models. It turns out that with BIC prime, if you have a difference of 6 or 10 between your models, that's equivalent to having a statistically significant difference, according to Raftery. BIC is said to be statistically equivalent to k-fold cross-validation for optimal k. How you ever get optimal k in the real world I'm not sure of, but you know, the derivation is somewhat complex. BIC is easier to compute than cross-validation for some model frameworks, but different formulas have to be used for different modeling frameworks, and there's no BIC formula available for many modeling frameworks. So if you want to do BIC on some of those things, like an artificial neural network, sorry, you're going to have to do cross-validation. AIC is an alternative to BIC. AIC stands for, first, an information criterion, ACACE 1971, and later, and somewhat modestly, ACACE's information criterion, ACACE 1974. It's nice when you're the one who invents the method. You can name it after yourself. ACACE's information criterion makes a slightly different trade-off between the goodness of fit and the flexibility of fit. It's said to be statistically equivalent to leave out one cross-validation. So AIC or BIC, which one should you use? Yeah, I mean, as we've talked about before, the difference between k-fold cross-validation and leave out one cross-validation is also a little unclear. And Powers says that the idea of looking for a single best measure to choose between classifiers is wrong-headed. And I would say the same is true about regressors. Regardless of what kind of model you're building, try to understand your model across multiple dimensions, and that involves using multiple metrics. So in the next lecture, we're going to talk more about cross-validation and overfitting. Thank you very much for coming to Big Day in Education. I hope you had fun today. I'm having fun. See you next time.